Okay, welcome everybody to this Analytics for the Better World seminar, webinar. So in fact, in the past, we already had some webinars, and I think the last one was already 1 year ago. And in that year, we also set up an institute, Analytics for the Better World. And we also decided to continue the webinars, the meetups. And today is the restart, and Lily Xu is the first one. And the idea is to have such a meetup every 2 months in the coming years. So it's a pleasure for me to introduce the speaker of today, which is Lily Xu. She's a PhD student in computer science at Harvard. More precisely, she's working in the area of AI and game theory. And I think the topics he's working on fits very well with Analytics for the Better World, because he's also looking for projects where she can have a positive impact on society. So today, I think, is also very an exciting topic. And she also received a prize for this research, the Informs Doing Good with Good OR prize in 2021. So Lily, the floor is yours.
Thank you so much, Nick, for the kind invitation to join your group. I'm really excited to be part of the relaunch of the seminar series, and it's wonderful to see more initiatives that are really trying to advance computation for societally impactful projects. So I'm going to be presenting work on using machine learning and sequential planning, dealing with issues of uncertainty with applications for wildlife conservation. So my work is motivated by biodiversity, specifically to try to combat poaching. Poaching is the illegal hunt or capture of wild animals, and it is one of the biggest threats to biodiversity worldwide, second only to habitat loss. One of the most primary methods of poaching is through passive hunting techniques, where poachers will enter protected areas and place wire snares to trap animals. So you'll see in this picture that there is a circular wire snare that's been set up between 2 trees. And then when an animal passes by, its head will get caught in the snare, the wire will close around the animal's neck, and the animal will be trapped there until the poacher comes back and then takes this animal for its meat or bones or ivory or whatnot. And it's a huge threat not only to biodiversity, but also ecotourism and the many habitats and populations that depend on wildlife. So one of the most prevalent methods to combat poaching is through ranger-conducted patrols. Rangers will enter protected areas and try to remove as many traps and snares as possible, as you see on the left, preventing wildlife from being caught in them. As they go about conducting the patrols, they'll carry GPS trackers recording where they've been and where they found illegal activity. And to make this problem a little bit more concrete, I'll focus on a case study of a specific park in Southeast Asia that we've worked very closely with. This is Sripak Wildlife Sanctuary in Cambodia, which is on the eastern edge, adjacent to the Vietnamese international boundary. This work has been in collaboration with the World Wildlife Fund for Nature. And to understand a little bit of what's at stake, Sripak is home to a very large population of animals, including Asian elephants, deer, leopards, and bangtang, which are these wild cows that are poached for their horns. And all of these animals are unfortunately targeted by poachers. So for Sripak, we have a large collection of historical patrol observations from when rangers have gone through this forest and collected observations of what they found. So for these 6 years, for example, of historical patrol observations, each data point, each brown dot here marks one GPS coordinate that has been marked in our data set. And each one of these may correspond, for example, to a biodiversity sighting where they found an indication of animals. They might have found and removed a snare, or they might have detected other signs of illegal entry, such as an illegal campsite where poachers were staying. And our challenge is to help rangers determine whether there are poaching hotspots that they're missing. So you can tell by looking at this map that the locations of historical patrols are very unevenly distributed. You can see that the brown dots are not spread out across the park, but that they're really clustered in certain regions. And you can probably guess just by looking at this map where the roads in the park are and where the patrol posts are, where they start and stop every patrol. And you can see that even in 6 years of historical patrols, there are many areas of the park that are left in green where rangers have never been even a single time in the past 6 years. So the challenge is that there might be very active poaching activity in those areas that rangers are missing out on. So what we're trying to do is leverage computational techniques, data analytics to help rangers better understand the poaching patterns in these parks and then help them plan patrols. To this end, the system that we have built is called PAWS, which stands for the Protection Assistant for Wildlife Security. And from a deployment standpoint, PAWS takes 3 main thrusts. The first is that we work very closely with conservation NGOs in order to design, develop, and implement the system. We've also evaluated our work through a series of field tests in Cambodia and Uganda, and we're currently working with Belize and other sites. And we're in the process of deploying this work globally through integration with existing protected area management software called SMART, which is widely used in conservation areas around the world. Simultaneously, as we're developing this PAWS system, we've uncovered new AI challenges that have not been addressed sufficiently by existing research, which is mostly focused on data-rich settings that have very, very quick time steps with long horizons, where we can collect a lot of data, really reduce our uncertainty, and then update our estimates rapidly. But in the real world, where we are very data scarce and our ability to collect data and update our models is very limited, we have to make sure that we are taking every possible advantage that we have in these real world systems from all sorts of domain knowledge through close conversations with domain experts to improve our AI models as much as possible to enable better and faster learning and performance. So there have been 3 main technical advances that from the AI methodology side that have come out through this work. And each of these 3 advances come in increasing levels of complexity as we, over time, come to understand the system better and better and understand what new challenges we ought to address next. So we first start with a supervised learning setting in which we're taking this historical data and trying to build predictions about relative poaching threat. Then we consider the setting in which we don't have a lot of historical data, so we have to proactively collect new data to update our model using online learning. And then finally, we consider a sequential decision-making setting in which our environment is no longer stationary over time, but rather changing as the poachers are responding to our patrols. And this change of behavior necessitates sequential decision-making. But because we have a lot of uncertainty, we have to make sure that planning that we're doing is robust to that uncertainty. So to start us off by looking at the supervised learning problem, again, we turn back to our historical patrol data in which we have these observations throughout the park. And then we discretize this park into 1 square kilometer regions. So each one of these pixels is a 1 by 1 square kilometer area in Sri Pak. And the dark blue areas are the places that have historically a lot more patrol effort. And then we're also able to isolate out the illegal activity instances in this data. So each of these dots, for example, corresponds to 1 location where they found snares. And then in order to make predictions on where illegal activity might be in the areas of the park that have not been frequently patrolled, we bring in geographic characteristics that we believe might be correlated with poaching. So these include geospatial areas, the information about the terrain, such as rivers, land cover, and water holes. And it also includes human-made features such as roads, villages, patrol posts, and the park boundary. And I'll also add that we have additional information such as animal density estimates from surveys that the park conducted, as well as dynamic features which come from remote sensing imagery, such as temperature and precipitation. So all of these features become covariates for a machine learning model. However, applying existing machine learning models out of the box is difficult in this setting due to very strong class imbalance, because most of the time when rangers patrol, they don't end up finding anything. So we actually have a 1 to 200 ratio of positive to negative labels. Additionally, we have a challenge of imperfect observations because wire snares are very hard to find, and each region in this park is still a 1 square kilometer area. So it's very possible that rangers might patrol an area and not observe anything, but it could have been there was a snare over there that they didn't see behind a tree, or they patrolled a week too early in a month, for example. So just because we have a negative label doesn't mean that that label is a true negative, which is a data complication that really befuddles our machine learning algorithm. But we're able to overcome these challenges and build predictions to predict relative poaching threat throughout the park. And each of these heat maps shows bright red in the areas where we think poaching is most likely to occur. And we produce separate predictions for dry ice season versus rainy season, because Sripak experiences very strong seasonality in which the rivers kind of flood over during the rainy season and become impermeable to cross, which really changes which areas are accessible, but then also changes where the animals are. So you see that poaching threat really differs between rainy season and dry season. One thing that I'll hint about, so without going into too much detail about how this is created, for the challenge of imperfect observation that I mentioned, the way that we're able to overcome this is we use as a proxy for the reliability of our negative labels, patrol effort. So if we patrol 1 kilometer and we didn't find a snare, we can't be very confident that there wasn't actually a snare. But if instead we spent a really long time and walked around like 10 kilometers within a single month in an area, then we could be much more confident that our observation of a negative label is a true negative label. So we use that intuition, that domain insight, in order to impute true negative label, impute true poaching probabilities, and then develop these predictions. And one more thing that I'll highlight is that you'll see that these predictions are kind of very dark red in various parts of the northeast corner, which is interesting because that contrasts with the historical patrol effort, where they've really not patrolled in that northeast region at all. So that's something I'll come back to later in this talk. But having built this pause system, we are integrating our AI system into the smart conservation software, which is the most widely used software system for protected area management around the world, and is used in over 1,000 protected areas across 100 countries. And there are some sites on SMART, such as Sripak, that have many years of historical patrol observations and therefore very rich historical data. But there are other parks on the SMART system, such as Royal Baloum State Park in Malaysia, that do not have very plentiful historical patrol observations. So we were actually talking with the folks at Royal Baloum, and we had shared, okay, these are the system, this is the system that we've built. These are the results that we've gotten in Cambodia so far. And they were really excited about it and said, hey, can you run these predictions for us as well? We said, yes, of course. They sent us their data, and we looked at the data set, and this is all that was available. So there really was not much information to go by, unfortunately. So we said, unfortunately, we're not able to generate any kind of reasonable predictions at the moment. But this interaction really gave us insight into our next priority area, which is realizing that for data-rich parks on SMART, we can leverage that plentiful historical information to build reasonably good predictive models to help with patrol planning. But in data-scarce parks, where we don't have a lot of historical observations, we need to simultaneously conduct patrols to detect illegal activity while also proactively improving the predictive model. So conducting patrols to detect illegal activity means that we have to exploit known hotspots, and improving the predictive model means that we have to explore areas with high uncertainty. And then this exploration-exploitation trade-off perfectly mirrors the key paradigm in online learning, which motivated us to use a multi-armed bandit approach. So that's what I'll introduce here. to set up our model, I'll just consider a toy instance of a park. So this is our protected area, and we discretize it into n different targets within the park, each with an associated feature vector. So each one of these targets has a set of features, such as what we've seen before about land cover and distance to road and distance to river, precipitation, and so on. And what we want to do is say for each one of these targets, how much patrol should we do in each region? And the key insight here is leveraging this idea about imperfect detection in the past, where we're using patrol effort as a proxy for the reliability of our negative label. This brings us the insight that if we patrol more, we're more likely to find illegal activity. And we analyzed the patrol data that we had from Shupak and found that this actually was the case. So each one of these lines is a different target in the park. And we are looking at the amount of patrol effort on the x-axis, and the y-axis is the probability of poaching. And indeed, as we increase the amount of patrol effort in terms of hours spent or kilometers walked, then the probability of poaching does go up, but with diminishing returns. So we don't want to just pick one area and use our maximum patrol effort there. We have to trade off and make sure that we're allocating our efforts throughout the park in a strategic way, such that we're maximizing our likelihood of finding snares. So our objective here is to find some distribution of patrol effort, beta, which is a vector, subject to a budget constraint. And we think of this budget constraint as the number of resources that we have in a given time period, such as 40 hours of ranger patrol in a given week that we can allocate. So what we want to do is we want to say, okay, you should spend 4 hours patrolling region A, 2 hours patrolling region B, and so on throughout the park. But unfortunately, there are a number of challenges that make this problem rather hard to apply traditional multi-arm bandit algorithms. So one is that we have a combinatorial action space. So not only do we have to pick some subset K of the N regions, but we also have to decide for each region how much effort to spend there. So it becomes this very large exponential action space. And furthermore, we also technically have continuous actions because time or amount of effort is continuous. So it's not just we do like A, B, or C, but rather we can go anywhere between 0 and 40 hours at each target. And additionally, and most crucially, because we are considering this real world setting, we really want to minimize our short-term losses. So traditional multi-arm bandit algorithms think about minimizing regret at an infinite time horizon. So we really analyze multi-arm bandit algorithms for their asymptotic properties. But unfortunately, in the real world, we don't have asymptotic time in order to wait. If we spend too much time exploring in the early rounds, that would correspond with animal lives being lost as we are not spending our effort exploiting and intentionally patrolling known hotspots. So you have to really make sure that we're limiting our exploration as much as possible. So in order to do that, we are able to leverage structure in the reward function, which I'll talk about. And we also have some limited historical data with which to warm start our algorithm. So with the reward function, what I'll mention here is we had seen these probabilities of finding a snare as a function of our effort. And then we can make a few observations about the structure of the reward function, which is our probability of finding poaching. So one is that this function is monotonically increasing. So as we exert more effort, we're never less likely to find a snare. Second is this function is relatively smooth. We'll say that it is Lipschitz continuous for some Lipschitz constant L. And then finally, we have that when we exert 0 patrol effort, we also have 0 probability of finding a snare. And that observation seems very intuitive, but is actually, as we'll see, very powerful in being able to simplify our uncertainty space. So to talk through our solution approach for this multi-arm bandit problem, I'll just quickly introduce, for anyone in the audience who may not be familiar, one of the most common paradigms in online learning. So with online learning, we're trying to learn estimates of some reward function proactively over time by collecting more data in an iterative way. So if we have two discrete actions, for example, let's say actions A and B, we are constantly maintaining some estimate of the rewards of A and B. So if we have no prior information, we can just say, we guess the reward of both of these is 0.5. If the reward will be somewhere between 0 and 1. But then, depending on how many times we've made observations of either A or B, that will impose a confidence radius that bounds our estimate to some 95% confidence interval. So here, we've explored action A many more times than we've explored action B many more times than we have explored action A because its confidence interval is much shorter. So with the UCB, the upper confidence bound method, we will prefer to take action A over action B because the upper confidence bound is higher than that of B. And the key intuition here is that if we explore action A, we have a possibility of getting really high reward, which would be awesome. But then even though we have a possibility of getting very low reward, it would still help us in the long run because we'll proactively reducing our uncertainty space as much as possible. So regardless of whatever the outcome is, either we'll get high reward or we'll just make our model much better in order to make better predictions in the future. And I'll point out that even if the empirical mean of the reward of action A is lower than that of B, we would still prefer to pick action A as long as the upper confidence bound is higher than that of B. So we would sample some actions from A, its confidence bound will shrink. The UCB is still higher than that of B, so we sample that action again until the confidence bound is below that of B, at which point we'll move to action B. So that's the key intuition behind UCB algorithms using this principle of optimism in the face of uncertainty. And then now to extend to our setting, I'll first talk about the challenge of combinatorial action space that I had mentioned originally. So if we consider the n targets in our protected area, and let's consider some discrete levels of effort. So we have m effort levels. If we're dividing this between like 0 and 10 hours, for example, there would be m equals 10 levels of effort. And our action space is unfortunately exponential. So we have m to the n number of possible combinatorial actions. And the way that we overcome this challenge is note that our action is decomposable. So not only do we have a reward for this entire vector beta, but we actually have a reward for each subcomponent of beta independently, because each subcomponent corresponds with the region in the park, and we'll know, did we find snares or not in that region? So we're able to reduce our exponential problem space to a linear m times n, which enables us to drastically improve our learning. So now, let's look at the m times n actions that we have, which is much simplified, but still very large and still requires that we do a lot of learning. Because if you consider, for example, 100 different targets in the park, and then m equals 10 levels of effort, then that is still 1,000 different actions that we have to learn good estimates about. So now what we'll do is consider, for example, one target that we'll call target 1. And let's suppose that we will patrol target 1 anywhere between 1 and 5 hours. And if we had 4 different targets in our park, this would give us 20 different actions possible whose reward we want to learn. But if we look at one target specifically, we'll recognize that if we have a good estimate of the probability of poaching at one level of effort, that gives us a reasonably good estimate of the probability of poaching everywhere else here. And this is where we're really bringing in those other characteristics of a reward function that we were mentioning, the fact that we have Lipschitz continuity and monotonicity, and that 0 patrol equals 0 effort. So now let's look back at our toy example, but here A and B correspond not with 2 generic actions, but rather it corresponds with our estimate of the mean reward for patrolling target 1 at either 1 or 3 hours of effort. So as it stands, with no additional observations from target 1, our uncertainty space for any amount of effort other than targets A or B could be anywhere in this green region. So with standard Bennett algorithms, we'll have to do exploration of everywhere in this green region and slowly bring down those uncertainty estimates in order to move from exploration to exploitation. However, because we have structured reward function, such as smoothness, we're able to leverage our Lipschitz continuity estimate and then impose that smoothness constraint over the uncertainty space. So here I'm visualizing, for example, a Lipschitz constant of 1, where the slope of this is 1. And that assumption enables us to prune our uncertainty space by saying that our upper confidence bound estimates won't increase in either direction by more than 1 times the distance between our UCB and any other region. So this Lipschitz continuity assumption enables us to drastically reduce our uncertainty space, leading to faster performance. But
Lily, may I ask you a question?
Oh, please.
Yeah, so it's already several slides back. So how did you come from the m to the power n to m times n? So I missed it.
Yes, thank you so much. So our combinatorial action space is this entire patrol allocation, which is a vector beta, which says for target 1, I patrol 2 hours. For target 2, I patrol 6 hours, and so on. So we have m to the n possibilities for what beta could be. But instead of thinking what this entire vector beta could be, we think of what beta 1 could be and what beta 2 could be. So by tracking not an estimate of the entire vector beta, but an estimate of the reward of each individual subcomponent of beta for each target, for each effort level separately, that enables us to only have to consider this linear set of reward estimates. And that's what we're visualizing here. So if we have n equals 4 targets and m equals 5 levels of effort, then that instead of having 5 to the 4 levels of actions, we only have 4 times 5.
That helps a lot. Yeah, maybe there are also other questions. So other questions. So please just use your microphone.
Please.
Other questions? If not, then so please continue, Lily.
Yeah, thank you. I think that was very important for understanding. So yes, we're looking right now at one specific target and considering the different levels of effort that we can exert there. And what we saw is that our smoothness assumption using Lipschitz continuity enables us to reduce our uncertainty space so we don't have to spend as much time exploring. And additionally, we leverage our other assumptions. So we had mentioned that when we exert zero amount of patrol effort, we have no probability of finding a snare, which again feels very obvious, but that combined with our Lipschitz continuity assumption is very powerful in imposing the smoothest constraint over our entire space, which then further drastically reduces our uncertainty. And lastly, the third observation that we made about our reward function is that it is monotonically increasing, which means that the estimate of the reward at B equals 3 hours of effort imposes a flatness constraint over anything that is less than 3 hours of patrol effort, because we'll never be more likely to find snares if we patrol less. So our monotonicity assumption further enables us to reduce our uncertainty space. So these things together, Lipschitz continuity, monotonicity, and zero patrol equals zero effort, took us from having this entire region almost filled with green with uncertainty to pruning out over half of that uncertainty space, which really enables us to spend less time exploring and more time exploiting areas that we know to be a poaching threat. One additional powerful observation that we have here is recognizing that our arms actually correspond with physical things in the real world. So targets 1, 2, and 3, and 4 are not just independent arms, but they're actually physical regions that are next to each other that have this associated feature vector, which means that if we have a good estimate of the reward at target 1, then that gives us some understanding of what the rewards at targets 2, 3, and 4 might be. So if we look at target 1, for example, this is our current estimate of the UCBs of the rewards. And we recognize that our Lipschitz continuity, our smoothest assumption, actually applies across targets as well. So if we now consider target 2, and let's suppose that we've never patrolled target 2 before, we have no idea what its poaching probability will be, which means that all we have right now is this estimate that 0 patrol equals 0 probability of poaching. But if we bring our Lipschitz continuity assumption and then quantify the difference the difference between targets 1 and 2, let's say that if we're just looking at the elevation between these two targets and it differs by some amount delta, like it differs by 100 meters, for example, then that combined with our Lipschitz continuity assumption enables us to transfer our reward estimates across targets as well, based on their similarities, which enables us to further prune our uncertainty space. So all of this together gives us some UCB estimate of every target in the park at all of these different levels of effort. And now we bring in a mathematical linear program to select our overall action. So now we go from these m times n different independent estimates to a complete combinatorial action, this vector beta. And at a high level, our mathematical program is to maximize the sum of our upper confidence bound estimates subject to our budget constraint. So this will give us like the highest possibility of reward that is feasible. So all of this combined, we call the lizard algorithm for multi-armed bandits, where lizard stands for Lipschitz arms with reward decomposition, and it is a new bandit approach that is really inspired and driven by the challenges that we face in the wildlife conservation setting. That also gives us like a nice broad generalization to other bandit algorithms more broadly. And furthermore, we're able to achieve really nice theoretical results in that the theoretical regret of lizard is theoretical no regret. So it's sublinear at O of t to the 2/3, and this actually improves upon existing regret bounds because we're able to incorporate both Lipschitz continuity and the combinatorial nature of the problem space. And finally, we also consider the empirical performance of our algorithm for a realistic problem setting in Tree Park Wildlife Sanctuary, where we are planning over a subset of the park. Let's suppose that this yellow region is the area that is accessible from a patrol post. And using real data that we have in Shriepak, we compare our lizard algorithm to a variety of existing bandit algorithms as baselines. And we see that our lizard algorithm in green drastically improves upon performance compared to baselines, but most particularly in the early rounds. So I'm considering here only the first 500 time steps, which if each time step is, for example, a day, then this corresponds with 1.5 years of patrols. So the other existing algorithms take a much longer to converge, which would be very devastating in these real world settings where that means 1.5 years of excess snares that are not necessary. We started with the supervised learning setting, considered, okay, what if we don't have very much data, which necessitated online learning? And now I'll briefly tease the third technical area that I had mentioned, which is to help answer this question: how do adversaries respond to our patrols? So you can imagine that we are enacting a patrol strategy that is really effective, and we're able to remove a lot of snares. And then the savvy poacher would recognize, hey, I keep coming back to this area. I keep, trying to catch my jaguar, and my snares keep getting taken away. So I should probably not come back here in the future. I should probably move somewhere else. So this reaction necessitates sequential planning. And by analyzing real data that we have from Merchant Falls and Queen Elizabeth National Park in Uganda, we observe two phenomena. So first is a deterrence effect, in which as we exert more patrol effort in one region in the park, the probability of illegal activity in that region goes down in the next month. But additionally, there's a displacement effect where as we patrol more in one region, the probability of illegal activity in the adjacent regions actually goes up. So this indicates that poachers are deterred, but then they're also displaced to neighboring areas. So there is this whole sequential dynamic environment setting. So the fact that we have deterrence necessitates sequential decision-making. However, the most prominent sequential decision-making approaches, such as reinforcement learning, require very accurate simulators of the environment in order to learn good policies. However, let's suppose that we have some estimate, of the strength of this deterrence effect, and let's suppose that we say it's 0.17, but because our data is imperfect and sparse, we can't be super confident that that parameter is exactly 0.17, but rather we might have much more confidence that it is within a certain range, let's say between 0.12 and 0.23. So what we want to do is sequential decision-making with respect to that uncertainty about the environment, which necessitates robust planning. And to do so, we introduced in our paper at UAI 2021, a framework mirror, which enables robust decision-making using reinforcement learning with respect to the minimax regret criterion. I'll stop there for the technical part of the talk and then move back towards what I know to be the big heart of analytics for a better world, which is social impact, sustainable development goals, and deployment. So I'll go back to the deployment side of this work on pause, starting with field tests that we implemented in Sripak Wildlife Sanctuary. So after we built our pause system and then generated predictions in Sripak, we want to evaluate, do these predictions actually make sense and are they implementable on the ground? And to do so, we set up a series of field tests in Sripak where we used our pause predictions to pick 5 regions that we thought to be a high risk of poaching, 5 at medium risk, and 5 at low risk of poaching, ensuring that all of these regions were infrequently patrolled in the past, so we weren't just relying on historical patterns. And also, we did not inform rangers of the risk classification of each of these areas because we didn't want to bias their patrols. So they conducted these patrols for a month in Sripak and then came back to us with their findings. And after looking at the data, we found that they observed many more snares in the areas that we thought were high risk of poaching and any fewer snares in the areas that we thought were medium risk and almost none in the low risk areas, which really showed that our algorithm is able to effectively discriminate between relative poaching threat. But furthermore, in a period where we are only going to high risk areas, the rangers in Sripak found over 1,000 snares in a single month, which contrasts with typical months where they were finding about 200 to 500 snares, which really show this large increase in performance. And we were excited about this, but we were even more thrilled when we received this email from Rohit Singh, who leads the Zero Poaching Initiative at WWF. Rohit told us, I am super excited with the results. Let's get this going on other countries too this year. So that's what we're doing by working with the SMART partnership, which is comprised of 9 different conservation NGOs, including WWF. We are building a new tool for the SMART software system that enables all protected areas around the world to run our pause predictions with as little friction as possible. So by taking the data that they already are collecting, that they already have uploaded and managed and sorted, enabling them to just hit some configurations, hit run, and then we'll do all the processing on our end and then send them back results like in this format that they're already using to really get at scale. And we're actually in the process of deploying pods throughout protected areas that are on the SMART platform. So we have worked in over the past year with sites in Central America, across Africa, as well as Southeast Asia. And we've been very, very grateful and fortunate to be able to work closely with a large number of conservation NGOs throughout this deployment process. And I also want to highlight most recently, we had the privilege of going on a field visit and running a 3-day workshop on PAWS in Rio Bravo Conservation Management Area. So this was a series of 3.5 days where we were going to the first site using PAWS in Latin America, and we presented the PAWS system, had the rangers like look at our patrol our PAWS predictions, compare that to like their intuition, and actually went on patrols every single day using our PAWS predictions, and found many instances of illegal logging, as well as a bullet cartridge that was used to hunt deer. So it's very exciting to us, and we're currently in the process of discussing with Rio Bravo how they might use PAWS like as part of their daily operations, which we're really excited about. But to pull things back a little bit, stepping to a higher level, what I hope you got away from this this talk is that there are many computational challenges in real-world problem settings. Data is ugly, data is messy, data is not there at all. So all of these real-world challenges gives rise to interesting computational challenges that really drive what AI and OR and data science should be focused on. So we need online learning when we don't have enough data. We need sequential planning when there is a changing and dynamic environment. We need robust planning in the face of uncertainty. And I didn't talk about this in this presentation, but we also need to consider like different objectives and different prioritizations. So it's not the case that we want to prioritize all animals equally, but rather some animals are more vulnerable than others, such as elephants are more vulnerable than deer, and elephants are located in different areas of the park than where deer are. So we really want a way to kind of prioritize species according to this ranking system, depending on their endangerment status. And our recent paper at ICHCA this year proposed this rank prioritization for multi-armed bandits. But the big message that I want you all to take away is that AI and and data analytics more broadly has much to learn from conservation and other real-world challenges, and that it's valuable, not just from the purposes of deployment and social impact, but it's also valuable from an academic and research standpoint to really work closely with this domain, understand what their challenges and limitations and possibilities are, and then design solution approaches to address and overcome those challenges. And to close off, I want to highlight a number of lessons learned throughout the process of designing, implementing, deploying, and scaling the PAWS system. So I have a number of points here, but to highlight two of them in particular. So the first is emphasizing the importance of incremental deployment before ambitious project design. So you'll observe that the 3 technical areas that I talked about, supervised learning, online learning, and then reinforcement learning, went iteratively more complicated, but started with like the simplest possible setting to make sure that we were sanity checking all of our assumptions, that we really understood the problem domain, that we were able to build up this relationship with conservation experts, so that we weren't just like doing something that was too computationally crazy, but was not actually feasible at all in practice. And the second is to consider real-world constraints as research challenges and opportunities and not limitations. So when we started talking to Roy Balloon State Park in Malaysia, and we said, oh, hey, we'd be so thrilled to collaborate with you, but oh, wait, you don't have very much data, instead of stepping back and saying, unfortunately, there's nothing we can do, come back to us in 2 years, that really opened up this entire new direction for research, which was to overcome that challenge that Roy Balloon was facing that minute, to proactively collect more data over time. So that's what I'll close off with. Thank you so much for your time and attention. I want to just finish by highlighting and giving thanks to all of my academic collaborators throughout the course of this work, as well as a large number of conservation partners who have been very gracious in sharing data and insight and time with us for this work. Thank you very much, and happy to take questions.
Thank you very much, Lily. This is really a very exciting presentation and really impactful work that you did. Fantastic. So I now ask for questions. So you can just use your microphone if you have a question to Lily.
I have a question, if I may, Dick.
Yes, of course. Yeah.
Hi, Lily, great presentation, exciting work. I was wondering if there are other areas you are thinking where the methods that you have used and the lessons you have learned from this application, you are also thinking of applying.
Yes, so I think that these methods are very broadly applicable throughout a number of environmental challenges. So not only for wildlife conservation, but also for illegal logging, illegal fishing, and adaptive management and protected area management more broadly. Certainly, a lot of this work can apply to any other settings, specifically when we have a lot of uncertainty and there's kind of spatial information. So if you're trying to predict where illegal deforestation might be happening, or resource exploitation, illegal mining, all of these things would be applicable with the system.
Thank you.
The detection of invasive species as well might actually be useful for.
I'm sorry, detecting
invasive species.
Invasive species, certainly.
Yeah.
Certainly, and all of these things, such as invasive species, really evokes this issue of sequential planning a lot more, and trying to understand how the dynamics of the environment are changing over time. Because particularly with invasive species, they can kind of like blow up in population. There's all these like cascading changes. So in these complicated real world ecosystems, when we make changes to one thing, it's really uncertain how those changes will propagate to the rest of the system. So I think addressing and overcoming these challenges of uncertainty in these environment dynamics to enable sequential planning really give rise to new challenges in robust planning using reinforcement learning, dynamic programming, and other techniques.
Other questions?
Yes, I have two. If I
yes,
may.
Claudia,
Yeah.
please.
So thank you, Lily. Really interesting. So I wonder that, for example, for data poor parks, whether you could focus on smaller zones, smaller sectors which do have more observations to start with, and then if that can motivate them to collect more data once they are looking at actual results that they are familiar with. So I wonder if that could be one option, and also now that you are that's one question, and the other one is now that you are expanding, and that's great in Latin America. I wonder whether how it will change for you now that, for example, you are working in areas with a completely different climate, for example, or whether the species that we're talking about and the trade for those species is different as well. How will it work, or how much modifications, how many modifications will you have to make?
Yeah, that is a fantastic question, Claudia. Thank you so much. So your first question about whether it makes sense in data scarce parks to focus on just planning in a smaller region. And I agree that definitely makes sense in the short term. But at the same time, if we're only focusing in a small region, that essentially means that we're only focusing our efforts on exploiting known poaching risk in a certain region, and then leaving everything else uncertain. So like doing no exploration in the rest of the park. So that really is not a sustainable strategy long term. Then we want to find ways of kind of making sure that we're distributing our resources throughout the park as well. But certainly there could be some balance between like, okay, we allocate a certain fraction of our ranger resources on the areas like the more fine-grained areas where we have more data, and then distribute the rest in the areas with high uncertainty separately. That kind of multi-objective optimization could be really interesting to explore. And for your second question about the how to adapt the system to new geographies, that certainly is an interesting challenge, and one that was particularly salient in our visit to Rio Bravo last month. So this was, as I mentioned, our first protected area in Latin America that we were working with. And one of the things that we were shocked to learn originally is that there's actually very little snaring happening in Rio Bravo. So even though there is poaching happening, just because there is not much snaring in the tradition, traditionally poachers will use guns for hunting, for active hunting techniques, whereas in Africa and Southeast Asia, there's much more a culture of snaring. So because all the illegal activity happening there is either logging or gun hunting, that really changes the situation in the landscape, because it's no longer snares which persist, and then if we see a snare we can remove it, but rather with bullet cartridges, with bullets and with illegal logging, it has to be kind of much more proactive, and deterrence matters a lot more there. That's much more priority rather than focusing on trying to remove as many snares as possible. So it really does change drastically between these parks, and therefore we're trying to think about what new algorithmic and planning solution approaches we have to implement.
Great. Other questions?
Hi, thanks, Lily. This is a great presentation. I'm going to have to relook at all my slides now after looking at yours. From a practical point of view, I agree. I think using as many tools as we have to help conservationists is vitally important. But sometimes we underestimate just how sophisticated our adversaries are. And one of the easiest ways, I'm speaking from a South African context, is where syndicates are able to sort of compromise the integrity of the park's information system and the strategies that the park is using. So I'm wondering, can you, or is one approach using these AI systems to look at, could you discover whether you have sort of information being leaked out of your park due to your strategies? Because I might set up a whole patrol strategy. The next day, that patrol strategy is given to the poachers. They adapt their movements, and is there a way of picking that up? That would be an interesting question, I think.
Yeah, that's a fantastically interesting question, David. Thank you so much for bringing up that notion of game theory and having like a organized crime syndicate that is much more of a strategic adversary, is much more closer to the full information setting, where they're really able to observe and do centralized planning. So certainly game theory would be a very interesting area to explore, and trying to understand this question of how are they reacting, and how can we proactively plan against that is very valuable. And unfortunately, the conservation biology literature and the ecological understanding right now is very, very immature in these regards to this question of how are environmental adversaries responding to ranger behavior. And the exact nature of this deterrence effect is not very well understood. And actually, one of my ongoing projects right now that we're very close to wrapping up is using causal inference to actually learn a causal effect between ranger patrols and poacher behavior. So what I had presented briefly to show deterrence was a correlational study, and right now we're trying to extend it much more robustly to this learning this causal effect, and hopefully that'll give us a much better insight into exactly what this adversarial reaction is like, and then therefore better inform our planning and patrol strategies. And of course, game theory and the kind of broader sequential decision making is the natural next step.
Great, thanks very much.
Other questions? I have a question, Lily. So, in fact, as a researcher, I think it's we make prototypes, But finally, to develop software that can be used in practice, that's another level. So how do you manage that?
With an army of undergraduates is the short answer. The longer answer is that it is hard, and I wish that there was better infrastructure and better incentives to enable effective engineering and building user-facing systems within academia. Unfortunately, academia just does not reward this, and there is no funding. There is no like publications that really support doing that kind of deployed work. So instead, we basically have to bootstrap. And this semester, for example, I am currently advising 4 undergraduates who are working on the systems engineering side of PAWS. So it is a slow process. It is not as quick as effective as full-time software engineers who are.
But you're doing it yourself with the help of students.
Yes.
Fantastic. Yeah.
So it's slow going, but I'm learning a lot in all directions.
I see. Yeah. Final call. Are there more questions? If not, then thank you very much, Lily. This was really very inspiring, very interesting, and yeah. So I would say keep on the good work that you are doing. And let's keep in contact in this.
Yeah, thank you so much. And thank you again to the audience for your attention and very thoughtful questions. I had my information on the slides, but feel free to contact me by email. I'm happy to chat and keep this conversation going.
Perfect.
Thank you so much.
The next ABW webinar is in November. But if you're registered, then you will receive the information about the coming webinars. So thank you very much, and see you in 2 months or so. Bye-bye.
Thank you.
Thank you very much.